Good. I'm glad it's Friday. I don't know, this week seemed really long for me, despite Monday. Because maybe Monday was half of it, I don't know. You guys got any grand plans for the weekend? Nothing. Gonna stay home, veg, sleep in, watch, and study physics. Oh yes, there you go.
Who's your team, man? What are you going for?
Well, I don't like the Broncos. I know, I was waiting for somebody to say it today. You're the first one. I don't have anything majorly against them. I lived in Colorado for 10 years. It was more the logo. When they changed to the new Bronco, I didn't like it. And Elway was good, but now he owns a dealership there, and I got tired of the commercials. So I don't know. It's more nothing to do with actual athletics. But anyway, is that who you're vying for, Thomas?
I don't really know the team, so
You go and do an activity? So I'll go for the food.
I go for the food.
Yeah. And the commercials?
Yeah.
Of course, you can watch them online afterwards, right? All right. We left off last time with the happy and sad balls. Just curious, did that pique anybody's curiosity enough that you thought about falling and going splat? No, not to try it. Thought experiment. So which one's the happy ball? Yeah, we started calling this one the happy ball. Whee, because he's happy. But I was trying to tell you right at the end that if you fall, you want to go splat or thud. You don't want to bounce. Remind us why? Would you rather have this happen to you than this?
Less force, more time. Increased time, less force.
Increased time, less force. Mostly. The end result is there's less force on you. That part's true. The time of the collision, they're probably actually fairly similar in the amount of time they're in contact with the table before either this one leaves or this one stops moving. It seems like, well, sure, it's still in contact, but the collision's over. So for the actual slowing down of that one versus the slowing down and re-kicking of this one. So I'm sure they are different a little bit, but it's not the dominating factor. But definitely the force on this is less. That's why we want this to happen to us than this. And two ways to think of it, as a reminder. This one gets stopped just like this one. They both get stopped the same. Do you agree? And that requires a certain amount of impulse, not force. Because that depends on the time. So since the times are about the same, so is that force. However, this one then rebounds and gets an extra kick to change its momentum now from 0 up to something back up. And so this guy's change in momentum is nearly twice as much as this guy's. Let me write that. Here's the ground, here's the ball. It's coming in with momentum down. It stops here. Still has that mass, but its momentum is 0. So we'll say this is initial. We'll just do an I. And this is final. So today we're going to do more collisions. So I wanted to spell this out. What's the change in momentum here? The change in momentum. How would you find it? The final minus the initial. What you ended with minus what you started with. So if it came in with this much momentum and ended up with this much, that'll give us the difference, yes? Well, it ends up with no momentum. It's the sad ball stops. So that's going to be 0. So the change in momentum is negative mv, whatever it came in at. So it's the same magnitude as what it started with. The change should be mv. I think you can see that. It came in at mv and stopped. So the change is mv in magnitude. But because velocity is a vector, I'm trying to remind you that momentum and change in momentum is a vector too. And this negative means this change in momentum, which is an impulse, was directed on this thing. Let's see. If this v we left as positive, unintentionally, but that means down is positive in this problem. You with me? So this negative sign means this change in momentum is directed upwards. The impulse is up. And that makes sense. It's the table up on the ball, right? So it changes its momentum in the upward direction by that amount, which makes it stop. Yes, Ron?
I don't understand why. If those balls are the same, you drop them from the same height, why does one bounce?
I was waiting for somebody to ask that. They're not identical. They're the same volume, same mass. They are made out of different types of rubber. And so molecularly, which we can discuss next chapter, this one absorbs that energy and it goes into other forms of like heat and internal breaking of bonds and does not come back. Where this one, it gets stored in the rubber molecularly, but it rebounds back like a trampoline.
But the impulse is the same for both?
No, the impulse is absolutely different for both, as I will finish.
Okay.
Yeah. But it's because they're different types of rubbers why we're seeing a different effect. Okay, so that's the sad ball. The happy ball continues on. It's got one more stage, right? It's up here, MV final. But if I started this one as positive, then this one has to be negative, correct? It's moving back up in the opposite direction. So we play the same game. The change in momentum is mv final minus mv initial. This one, though, has a different final velocity, momentum, than the one that just stops. So he is negative mv minus the original. So you see the two minus signs? Minus plus a minus is going to give you minus 2. Now, an assumption I'm making here is, as you can probably see, the speed it comes in at, ideally, is the speed it bounces back up at, if no energy is lost at all. And just to keep things simple, that means this v is the same as this v. It comes down at the same velocity it bounces up at. So that's how we get its change in momentum is twice as much as the sad ball. And remember, this is impulse. The impulse provides that change in momentum. There was a force for a certain amount of time. There was a force for a certain amount of time. Since the ball that bounces receives twice the change in momentum, it has twice the impulse, twice the force is involved. This F is a lot bigger than that, given that the time of the collisions is almost the same. If that varied, then things could change. But I'm trying to keep it simple for the things that bounce in general, or rebound. Yeah, Barbara?
If you knew how far up it bounced, you could calculate how much momentum you had.
How much momentum you had? I know where you're headed with it. If you could calculate how high.
Exactly the same as you twice as much.
Exactly. I didn't plan that. But yeah, well, we'll just do it this way. Yeah, if you start here and it bounces, boom, boom. In reality, things kind of bounce like that, right? It doesn't come quite as high as it with each bounce.
But without air resistance, wouldn't it?
Yeah, there's several things that cause this, and that's next chapter, so very good. See, this is why they make these textbooks in this order. You're starting to think, this is great. So ideally, yes, it would come up to the same height. And if this velocity are exactly the same, it would come up to exact same height.
If we could calculate if we knew the distance of bounce
There you go. Yeah, if we knew this height, the initial height, and we know this height, yes, absolutely. The difference there is how much, well, you can figure out how much energy it started with, and those formulas are coming next week, next lecture. And then this one, it returns with a little less energy. Where'd that energy go? Some is air resistance. A lot of it's heat molecularly down here. Sound is a form of energy. Some of it can go into that. I'll tell you now, total energy is always conserved. You can't create it or get rid of it. Total energy is always conserved. But you have to look at your systems. And so if you're just looking how much energy the ball starts with versus how much is left in the ball here, some of it left the ball at some point, and it's no longer with the ball. So the ball can't return to its original height. And that difference could precisely be figured out by these H's. Absolutely. So, there you go. So in my mind, even though I biased you by saying this is the happy ball, now we really know this is probably the sad ball. This one's happy because he felt half the force. So yeah, go limp. Relax. Less stress in life if you relax, right? So there's a collision. Let's do another collision. This is an air track, and it's like a big hockey table. It's got lots of little holes that we blow air out to minimize friction. And so this will kind of glide along. And so without friction to slow it down, inertia says it'll just keep going until a force acts on it, the ends to redirect it. But it takes a long time for it to lose its speed or its momentum. So it can keep going. It's just so we don't have to deal with friction right now. Well, got a little slug here. Oh, I forgot my pencil. Let's see if this works. We'll use gravity. I'm going to pull a plunger back, spring load this, and then drop this in here. So the idea will be, I'm going to burn the string. It's going to release the energy that's stored in it, and it's going to shoot the bullet that way. What will happen? The card will move backwards? Good, yes it will. Why? Very good. Newton's third law says, yeah, the force the cart or the cannon exerts on the bullet is the same exact force the bullet exerts on the cannon. Cannon, bullet, bullet, cannon. Yeah.
Would it be safe to say that the sled probably wouldn't be going as fast as the bullet though because it has more mass?
Very good. Newton's second law. Since the slug, the bullet, is a lot less massive, for that same force, the small object will accelerate more and come out faster than the cart because it has more inertia. Absolutely. What else can we say?
The cannon will keep moving after it's fired the bullet as long as we don't have external force.
That's right. Once the bullet's shot out, that recoil force, the kick, will get this moving. But then Newton's first law says it'll keep moving until it runs into the end. Something else happens. Good. What else? See how this all comes together? What's our new topic? Related to that. Okay, momentum. Good. The impulse is the same. It comes from Newton's third law. If the force is the same between them as it shoots it out, well, that's going to be the same amount of time for the bullet and the cart when the spring's acting, just like the marshmallow and the PVC pipe. So yeah, the time's the same, the force is the same, the impulse is the same for both. An impulse causes, or what comes with an impulse? A change in momentum. So it's going to change the momentum of the cart and the bullet. What's the momentum now? 0. What will it be after? You just told me both will be moving. So this guy will have no momentum?
No, they have this.
He'll have momentum? And he'll have momentum?
Yeah, but they are offside if
Very good, very good. So if you have a simplified version. So before, this is called conservation of momentum. In other words, total momentum is always conserved. If we're looking at the cannon and the bullet, that's our system. We're looking at both of them, then their combined momentum before the collision has to equal their combined momentum after the collision. Just like with the table and the ball. But I think I like this one better. So, what's the slug's momentum initially? 0. Let me write it out this way maybe. Let's do initial. So this is total momentum before. Okay, so what's the total momentum before? It's the mass of the cannon and the mass of the slug. Well, that one, yeah, it's easy. This one's not moving, this one's not moving, so yeah, the total momentum of the system is 0. Okay, well that automatically should tell you, no matter what happens after it's shot, the total momentum is going to be 0 also, because it can't change. So afterwards, we have mass 2 moving with some final velocity, and mass 1 moving with some velocity this way. So the total after there. So this is generic. The total momentum after is the cannon's mass, however fast he's going. But that's going to be negative. We already know that, don't we? But say you don't. Maybe you're not sure. If you solve for this, because you know everything else, and it comes out negative, then you know. And the mass of the bullet moving with this speed. So that has to equal 0. Let's do it and see. You can probably guess already, though, approximately how these two are going to move, can't you? You already said it based on Newton's second law. The bullet should be going faster and the cart's slower. But do you see that? If this velocity is higher, the bullet, then a lot of the momentum might be here. But he doesn't weigh very much. Well, that's why he can move faster. The big heavy cart won't move as fast. But he'll still have a lot of momentum because he's big and heavy. But total, they're going to be 0 because one's going that way and one goes this way. So yes, the cannon's cart will be negative. Okay, enough talk. It's not perfectly level. And there it recoiled. It's a tiny little bullet. And there its inertia keeps it going. No reason to slow down. But doop-de-doo, doop-de-doo, doop-de-doo. You get the idea there. Put in some numbers. I'm making these up. So we know that mass 1 v1f has to equal mass 2 v2f. So the momentum of the bullet one way and the momentum of the cannon the other way, the magnitudes have to equal. So if the cannon is, 100 units, and the bullet is 5 units, you know the ratio of the velocities, don't you? It's going to have to be the same ratios, whatever you make it up to be. Let's say the bullet's cruising along at 20 units. So it's a small little thing, 5 units going 20 units that way. How fast is the cart moving? Exactly. So it only moves 1. And that's why you see the bullet shot out really fast, but the cart was just kind of trucking along. They still have the same momentum, just in opposite directions. because the total had to still be the same.
This one implies when there's no loss of energy or friction.
This applies in any collision. If we did this with friction, as soon as the collision's done, you got those other forces acting, and you'd have to include those. So say we did it here. Because the force of friction is large enough, it'd shoot it out, and you probably wouldn't see this thing move at all. Because you saw how slowly it wanted to move. Friction would hold it back. But you could compute that force of friction because you know how fast it was trying to move.
But then we have to have another M3.
Yeah, you'd have to throw more into it, and I was keeping it simpler.
How would you measure friction in terms of mass?
We did friction before. It's the support force, the weight of this guy. Down. It's supporting that. We didn't cover how to solve friction ever, so, and I didn't intend to. But it has to do with this guy's weight and the support force. Let's do another one. Let's do an elastic collision. I'm going to teach you the two types of collisions. There's elastic and inelastic. And we'll use those for this chapter and next. This is elastic. That's where they bounce off. They kind of rebound. Ideally, a perfectly elastic collision is no energy is lost at all, which there's no such thing, but this approximates pretty good. So they come and bounce. So you can send them down. They come back together, have a collision, boom, and exchange momentum. Okay, these are roughly the same mass, same size. So if this one's at rest, and I let this one come in with some momentum and collide with this one, what will happen? Which one will move? This one will get moving. What, will this one stay moving? How do you know it'll stop? Will it rebound or keep going or stop? There's three options, right? It could bounce back, it could keep going, or it could have a dead stop. Now this one we'll do first, then I'll calculate it. What do you think? Who thinks it'll stop? Who thinks it'll keep going? And who thinks it'll bounce off? All right, so the stops have it, but the bounces are next. Okay. So I'll try to keep this one from coasting. It stops. And then if that one goes down, stops. We'll just simplify before, after. The momentum before has to equal the momentum after. So we have m1 v1 plus m2 v2 equals m1 v1 plus m2 v2, where these are the after velocities and these are the final or initial velocities. All right, what's the momentum of cart 1? We'll call that this one. Something. mv. It has a velocity. What's the momentum of this one? Yeah, 0. So the total momentum of our system to begin with is just due to this cart. He has all the momentum in our system at the beginning. All right. Afterwards, well, these could come out at, this one could be moving or that one could be moving. This could be solved, right? You could split the total momentum up, couldn't you? Maybe this cart gets half the speed and this cart gets half the speed. Why does it work out that it stops?
The masses are the same?
Very good. Good observation. All these masses are the same. So if m1 equals m2, let's just call these m. They're all m. If you divide everything by m, it goes away. And you're left with, in this case, the initial velocity of that cart gets split up. Still not quite enough info, is it? Which is your teaser. In an elastic collision, like this, kinetic energy, if you've heard of it, well, I haven't told you what it is, but it's the energy associated with motion, is also conserved. And you would play a similar game and you'd get two equations. And the only way both of those can be met, that momentum's conserved and kinetic energy is conserved, is if the first one stops. It's just another condition energy puts on that we haven't covered yet. But this is how you do it. The total momentum before has to be the total momentum after. So look at it this way. This guy has all the momentum initially. Afterwards, if he stops, which he does, doink, what's the speed of this guy? Whatever speed that came in at, because they're the same mass. Momentum's conserved. Because if he stops, this guy now has to have all the momentum. So it'll have whatever momentum this guy started with. Boink. Yep, now it's all over there. It's transferred. There was an impulse. Boink. What if it's half the mass? What do you think will happen now? Is this guy going to get all the momentum? So you think it'll share? All right, will they both move this way, or do you think this one will bounce off? See, your gut will help you solve these problems. You know what's going to happen, but if you want to know exactly, you conserve momentum and energy and find out. Well, let's see. He's coming along. I'll try to hold this one still till he gets here. There we go. Now I want you to be good scientists and make an observation. This guy's speed after the collision versus this guy's speed. If I can move that one roughly the same. Versus difference? You can tell he's faster. Well, sure, he's got less resistance, inertia, mass. So yeah, more momentum, well not more momentum, but more speed goes to him. The same momentum's transferred because this guy is the same. He hit this guy. However, this guy kept moving too. But now watch his speed before and after. So he comes in about this fast. After, slows down. Well, he better, because if he's transferred some of his momentum to this guy, he's lost some. He hasn't changed his mass, so it shows up in speed. And he ends up going a little slower. What if I do it this way? And let the small one run in? What will happen? Will this guy move at all? Notice he's not going as fast as before, is he? Because he had to stop him and turn around. But this guy ended up going a little faster. But the total momentum still has to be the same. What's the total momentum now? While this guy's moving. Yeah, he has it all. So his mass times his velocity. Because this guy's momentum is 0 initially. Afterwards, boom. Now the total momentum is mv plus mv. But one of them's negative because they're opposite directions. They have to share that total momentum. If I held this one still, what will happen to this guy? Comes in at that speed, goes out at that speed. There's an ideal bounce, mostly. As ideal as I can get it. All right, how about an... Oh, I need to do this one first. Okay, these two are tied together. There's Velcro on this end. So they can stick together if they come back. But there's a spring in between. So the spring's going to exert a force on both of them. They're the same mass. What do you expect? All right, how's the force going to compare that the spring pushes on each cart? Should be the same. Newton's third law. It's the same spring. So they should feel the same force for the same time. So they'll receive the same impulse, which will try to change both of their momentums. They're the same mass. So how do you think they'll spread apart? What? You don't think they'll spread apart? The spring's going to push on them. It's going to push on this one that way, and it's going to push on that one that way. Because I've compressed the spring and tied it together. I'm going to burn the string and let the spring push them apart. So they will move. They'll recoil. How do you think their velocities will compare? What's the total momentum before this collision? 0. What will the total momentum be after they start moving? 0. Okay, they're going opposite directions. So one's positive, one's negative. They're the same mass. So they're going to have to move the same speed. All right. Yeah, they look about the same speed. Then they come, and now they're going to have a collision. Boom. And they stop. Now that's called an inelastic collision because they didn't bounce off each other. They stuck together. And in that case, we're going to learn the kinetic energy was not conserved. Kinetic energy. Total energy is always conserved, but kinetic wasn't. But we're not there yet. Total momentum is always conserved in both types of collisions. So for momentum, it's always conserved. Kinetic energy, it'll depend. So, why did they both stop? You have M1, V1 before. They're coming at each other, right? And it's the same velocity. We established that. Plus another one. They're the same mass. They're the same velocity. But one of them's negative, right? Because they're coming opposite directions. Do you see that this is the total momentum before they collided? As they were... Oh yeah, air's not on. Before they came together? So the total momentum is 0. We established that because it was before we started. It is while they're moving. It is when they come back. That's where we're at. So when they collide again, it has to be 0. Whoop. In this case, in an inelastic collision, they stick together. And so you can think of that like this. The two masses are together trying to move. It's like tackling someone. You're now stuck with them and you're moving together. Or you catch a baseball. You and the ball are separate, but once you catch it, that's an inelastic collision. You're together now, and you move together at some speed. So in this case, it's 2 mv. But wait a minute. The total momentum before was 0, so it can't be moving. The velocity will be 0. And that's why they do a dead stop. You guys grasping this? Let's try then an inelastic one with a smaller. No, not yet. Let's do it this way. Same idea. We're going to have this one come in. Same mass. What will happen now though? They're going to stick together. Okay, yeah, it'll move this way. Your gut tells you right. This guy has all the momentum, so the total is mv plus his 0. They're going to stick, and the combined mass is going to try to move. How will the speed of them together compare to now? Yeah. See it slow down? And if we measured this, I don't know if you can tell, but the speed that guy's moving now to now, yeah, it is half. Because we've just doubled the mass, so the velocity has to get cut in half. I always like trying this. If I can push them at the same velocity and give them the same momentum, oh, dang it. No, not bad. Okay, who had more momentum? Yeah, this one. He had a little more momentum than that guy. So when they came together, they have a combined momentum that went this way. So together, right now, the total momentum is a little more than 0 because he was a little faster. And I tend to flick a little harder with my right hand. Now let's try small guy. Okay, what'll happen? Yeah, good. It'll go that way because they're going to stick. But how do you think the speed will matter now? He didn't have as much momentum as this guy because he's smaller, assuming I'm flicking them at the same speed. So when they combined, they didn't go quite as fast as with this guy. But we can go the other way. This is more fun, I think. Now what'll happen? This has more momentum coming in than this one does for the same speed. So they'll go that way. But see, it's faster now. Because we started with more momentum initially. Oh, is there any other combinations to try? I don't know. So let's throw in some numbers. Let's see. Let's say these things are too light. So momentum after, momentum before. If this is seeming redundant or like, oh yeah, we get it. Oh, even physics students in the calculus-based classes, they forget this. And you don't know how to set up your problem unless you remember that the total momentum is always conserved. And so what they usually think, oh yeah, I got it. And they start plugging the numbers in and they forgot one. So I always like to write them all out. We got 2 carts before, we got 2 carts after. Sure, some of the carts might not be moving before or after. But if you overlook that, you might get it wrong. And a lot of them do. So yeah, that's what you do. All of them before, all of them after. Let's say we have this case where he's going to come in. So let's give some numbers to these. Let's say mass 1 is the lighter one. We'll say, let's call him M, and this one 2M, to keep it easy. And that's about what it is anyway. So this guy, if this is M, then he has twice that mass. Let's say he's coming in with, let's pick a speed. How about V? This guy initially is not moving. So that's going to go to 0. This will move after, and this will move after. Let's see what we can figure out. Are you with me so far? So little guy's coming in. Big guy's not moving initially. They're going to bounce off each other. They're both going to move. We saw that, but can we figure out how at all? Let's divide everything by M, because we don't need that. And we have the initial velocity of that little cart has to be, there we go, 2v2. So it helps give you a ratio. And the energy will come into play next chapter. But that's as far as we can get at this point. If I give you any of those velocities, you could solve. If I actually gave you values. It came in at 10 meters per second and bounced back at 5 meters per second. I'm making it up. What would the velocity of the big cart be? Subtract the 5 off that both sides. You get 5 equals 2v2. Divide by 2. V will be 2.5. Do you see that if it was 2.5 and you doubled it, you get 5? So yeah, if this one came in at 10 and bounces off at half the speed, you know exactly how fast this will be going. You have some homework problems like this too. I gave you a couple. The author likes a big fish eating a small fish. But it's just two bodies coming together and colliding. If you eat a fish, what type of collision is it? Yeah, it'd be inelastic, but momentum's still conserved. If you ran into a wall with your car, what type of collision do you think it'd be? You're going to bounce off the wall? You'll probably crumple and destroy the wall. So yeah, it's pretty much inelastic. Yeah. But if I throw that rubber ball against the wall, what type is that? Yeah, that's elastic. Just to start learning the differences here. It'll matter more with energy. But total momentum is always conserved. So you just find out their total momentums before. It's got to equal it after. Solve for whatever the one unknown is. They'd have to give you enough of the rest. I will. Yeah.
Did you say elastic was concentration of energy in general or just kinetic energy?
Kinetic differs. We're going to learn kinetic energy is the energy associated with motion. And we've already kind of discussed it. Barbara brought it up that when things bounce, they don't rebound with as much kinetic energy as they came in with because some of that energy got transformed or transferred into a different form, like sound, heat.
Right, so elastic, those terms only apply for kinetic energy. Is that what you're saying?
Those describe collisions.
But since energy is always conserved.
Total energy is always conserved.
So that's only for a system.
Yeah, these are for whatever system you're considering. Yes, absolutely. What I'm saying now is total momentum is always conserved, either type. What I'm trying to give you a heads up for, those of you that read Chapter 7 maybe over the weekend. Kinetic energy is not conserved. Total kinetic energy is not conserved in an inelastic collision. Because in order to stick together, some of that energy of motion, kinetic energy, will be transformed into some other type. Energy to smush your car, or molecularly, or friction, so there's a lot of heat. And so that energy goes somewhere else into something different, and it's no longer in the object as motion. However, total energy is conserved. If you count that energy it turned into, heat that left the system, well sure, that's got to be equal to what you started with, always. So that's just a teaser for kinetic energy next lecture.
On the impulse, when the two went together and they stuck together.
Yeah.
The impulse was the same, but the force went down?
Yeah, if they're coming together and hit each other, boom.
Right.
Yeah, they're in a collision. Okay, this exerted a force on this exerted a force on this. Newton's third law says they're equal. Well, they're in the same collision, so it's for the same time. So the impulse is the same for both of them also. Thus, this one exerted an impulse on him which caused him to change his momentum, and vice versa. Since they had the same momentum coming in, because they're the same mass at the same speed, for that case, it had the same effect and made them both stop.
When it sticks together but moves.
There you go. What do you think? When they collide, how do the impulses compare? So this one's stopped, this one's coming in, right there. There's an impulse. Okay, I'll walk you through it. You know this. I think you just, what's your gut tell you?
My gut tells me that the impulse is the same, but the time...
But something else is going on. Well, good gut. I bet before physics class you would have said it's not the same, but I've harped Newton's third law into you enough. Good. Well, yeah, this hits this. Reaction hits back. Equal and opposite force. It's a collision. They're both involved at the same time. So even though there's a different scenario, like this, and they started moving, during the collision there was the same impulse. So they both received the same impulse, the same change in momentum. What's different, though, is how they react. If the force was the same, the time was the same, the impulse the same, change of momentum is the same, but they had different momentums to begin with, right? This guy's momentum was mv coming in. This guy's momentum was 0. They have the same change in momentum. If they're going to have the same change, this one stopped. Well, when they bounced, do you remember that? Start there. When they bounced, this guy had a dead stop. So his change was mv to 0. Change, mv. So his change had to be mv. Since he started at 0, he ends up going mv. Same speed that that one came in at. Similar thing here, it's just the m changes because they're now moving together. It's 2m. But the change in momentum for each, before and after, this is your system after though, both, has to be the same because it was the same impulse. A lot of people miss that. Good observation. Does it make sense? You're like, yeah. Okay. Yeah, I encourage you. This is one that doesn't come quite as easily to most people. So work some of those problems out in the book. Look at the check your understandings. I think we have time. I wasn't going to ask you that many. Grab your clickers out. I'll ask you at least one or two. Oh, yeah. All right, it's coming up. Session IDs in the lower right, like before. Polling's open. Start entering when you're ready. I had 2 or 3 questions prepared. We'll just see how many we get through. Your homework is due Sunday this time for most momentum stuff. Give you a moment to log in and answer that one. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 30 players today. Most of you think A. Good, you remembered that. Very good. The mass doesn't change, right? That's the key here. All right. Okay, here's a collision for you. Big fish comes up and swallows a small fish. This one's conceptual, no numbers in there, but you ought to be able to know at least what's going on this much. So this is like the big cart running into the small cart. What type of collision? Inelastic. They stick together. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, 87% say B. The answer is B. Good. Very good. Any confusion there? Those of you that missed it, now you know the right answer. Would you like another explanation? Then one more. Same kind of setup, but I'm not asking you about the speed. I'm asking you about the momentum. Ten, 9, 8, 7, 6, 5, 4, 3, 2. Oh, we got an extra player. 1. 2/3 of you think it's A. Very good. The total minimum before has to be the total after. Who has all the momentum to begin with? Big fish. Afterwards, they're together, aren't they? So their total momentum still must be the same, because total momentum is always conserved. It's just the little fish is part of the big fish now. All right, have a great weekend. I posted those, so you can see what you got on exam day, and your retake was there. Yeah, so if you took both, the average will be your grade.